In today's video, I will be explaining how to solve the problem a rectangular bond. So in this problem, it's very similar to one of the previous questions where we are asked to find the largest square, but this time we're asked to find the largest rectangle. So we basically have a few obstacles here inside this grid, and we have to find the biggest rectangle that we can form without overlapping any of these grids that are blocked off. So let's draw this out here and take a look at how we can solve this problem. So this is the example grid. We have one block here and one blocked off here. So this one and this one cannot be used. So here the biggest rectangle should be this part. And let's consider how we can find this in O(n) squared time. So we can sweep through each of these rows, or you can also go through each of the columns depending on they both work the same way. So here let's keep track of a array, a 1D array for each of these columns and rows, and it will keep track of the longest length that we currently have for each of these rows. So for example here, for this first row, the longest length will be 1, 0, 1, because here this is the longest length that we currently have, and then here this one's blocked off, so it will be 0. The longest length that we can have will be 0, and here it's 1 again. And then for this row here, it should be 1, 2, 3, because there are no blocks that are blocked off, so all of them can go in a straight line. So we're looking at this first grid first. So then this one is just 1, and then here it's 2 because we're adding onto the previous one, and then here this should be 3. So this is a total of 3, and this is also the same. This will be 0, 1, 2, and then the last one would just be 1, 2, 3, like so. And we can think of these as heights. So let's look at this column first. For this first row, we will look at the columns first. Our heights will be so we can contain this inside an array. So it's basically equal to, the first one will be equal to 1, the second one is 1, the third one is 0, and then the last one is 1 as well. So we can basically take a look at this and find the biggest rectangle that is connected. So here the biggest one will be these two ones added together, which is 2. And we can go through this using a monotonically decreasing stack. So monotonically increasing stack. So we want to keep this stack in increasing order. And to do this, we can take a look at each of these columns that we have. So start at the first column, we will use a stack to keep track of this whole thing. And then we're gonna use another, so then basically here, first of all, we have a stack, and this first part is still the same thing. It will first be 1, and then we look at the next one, and it's also 1. So here these two ones can connect to each other because it's equal to these two, so we can connect to each other. Or we can think of it in another way. Let's just look at a few more columns first, so this way it will become easier to think about. So let's look at the second row. In here, the second row will be 0, so 0, and this one will be equal to 2, this one's equal to 1, and this one's equal to 2. So here we can think of these as rectangles, so we can erase these first. Now let's take a look here. We can think of these as rectangles. Here, this one will have a height of 0, this one has a height of 2, this one has a height of 1, and this one has a height of 2 again. So here we can look at each of the rows or each of the columns, and we take a look and see if the previous one is smaller than it or greater than it. So first of all, we'll have as normal a stack, and it will first contain the first value, which is 0, and then we'll look at this next one, which is equal to 2, and we see with the previous one, is the 2 smaller than our previous one? It's not, so we don't have to do anything. We just continue to the next value, but we add this into our stack. Now we're looking at this one with 1. So this one's 2, this one's 1, and this one's 2 again. So we're currently looking at this rectangle with a height of 1. And this rectangle, we can look at the previous one. It does have a height greater than this current one. Well, it does. So this rectangle is taller than this current rectangle. And so we should see how long this current rectangle spanned. So for example here, if we have a few more rectangles out there, we can, let's just say we have a few more over here and a few more over here. We would just take a look at how long this rectangle spanned. And this rectangle would remove everything, this rectangle here would remove anything that's basically taller than this, because we're going to use the same calculations. So if this is a rectangle before it that is taller than this, then we are going to see what is the maximum triangle we can get when we consider this side as the end of this tall rectangle. Because this is we know that this will definitely be the end for this current tall rectangle, because it cannot stretch on anymore since there's nothing here, because this rectangle only has a height of 1. It will not be able to stretch out anymore through this part. So this will definitely be the ending point for this rectangle, no matter how long it spanned out there. So we're going to look at how much it is out there, so how long it will be out there. And what we can do is look at an element before this current element. And so we should keep track of the index basically. So this we can see have an index has an index of 1, 2, 3, and 4. So now we have these. Our current index is at 3. So we're looking at our previous index because we're starting at this. We're basically ending at this 2 index, and we want to see where our starting index is. So our starting index is just the next element inside this array, because inside the stack, because it is the other element that is shorter than our current element, because we will remove it if it's taller than our current element. So we should see the first element that is shorter than it. So it's at element 1, so it's the index 1. So we get the difference between these two. So that will give us 1, I mean, but here, so we basically get the length of that. It's equal to 1. So this is the width. The 1 will be equal to the width, and then the height will be multiplied by whatever this element is. So here we get 1 times 2, so our current maximum is 2. So we're basically looking at this rectangle here. So this is 1. This gives us 1 rectangle now. But we have to pop this from our stack because it's greater than the current element that we're looking at, because we're looking at element with this height 1 and it has a height of 2. So here we pop this back and we check with the previous one again. So we're looking at this index 3. So 1 is greater than 0, so we don't have to pop 0. We can leave 0 there. And now we're looking at this index 4. So here this 2 is greater than 1, so we should also leave 2 here. But this isn't the end of this search yet, because here, as we see, the biggest rectangle should be this one, which has an area of 3. And to do that, we can basically think of another rectangle here with also another index, but with a height of 0. So this 0 will definitely be smaller than everything we have here inside, smaller than or equal to everything we have here inside this current rectangle, because our values cannot be negative. So this will definitely be the biggest that we have. And so here we should add this, so then we'll pop everything that we currently have. So we basically want to add this 0 in here, but first we will check with everything that we have in this current stack. So we have one with length 2, with height 2, which is this one. And of course it's bigger than 0, so we should pop this 2. But also we have to see what is the largest width that it spans. And the largest width is just the index of the previous value in the stack. So this is basically the starting point. This is the largest width, and our ending point is here. So we basically end at 4 and start at 3. So this also has a length of 1. And 1 multiplied by 2 is 2. So our current area is 2. Our maximum is already 2, so we don't have to change anything. So we basically pop this out. Now we want to look at the next value. So the next value is 1. So here this 1 is still greater than 0. So we should get the index again, but we should, so every time we look at these indexes, we should start with this current index because we can pop multiple times. And we know that since our stack is basically going up in this order, because we're always keeping track of the ones that are greater. So so basically currently in our stack we have these values. This one value, and then this value is gone now. This 2 value because we popped it. So now we have another this value at 3, 1, and then we just popped out this value at index 4. So now what we're looking at now is this value. But since we're starting here at this 5, we know that whatever is in between 4 and 5 must be greater than 1 because our stack was increasing. So we should, only the indexes that are inside this current stack should be greater than 1 because it's increasing in this order. So this 1 can definitely span outside to here because anything with a height of 1 should be included in anything that has a height higher than 1. So we should always look at our index like this current element that we're looking at, not the index of the stacks, because the stacks can be popped out and then it will be smaller again. So here we are looking at this index 5 and this index 3. So we can think of so we're looking at 3 right now, and our ending index is basically at 5 minus 1. So 5 minus 1 is here. We're basically ending at this 4, which is correct because our biggest rectangle here is just expanding to here. So here we should pop out our 1 and basically get the index previous to that is smaller than 1 because our stack is increasing in order. Notice how here, since we already popped out this 2, it is correct because the next element we're pointing to this 0 height at index 1. And so when we're looking at the index 1, this will represent that 1 is basically the starting position of our of this rectangle with height 1. So here, since we're starting at 4, because we are getting this current position minus 1, so we're looking at 4 minus 1, so this gives us the width of 3. And so this gives us basically the width, which is correct because here our rectangle with a height of 1 can be basically like this way. And that has a width of 3 and a height of 1. And so here our maximum rectangle will have an area of 3, 1 times 3. And this is just like the area that we just calculated here. So this is what we can do every time. We just keep track of the total height. And every time we meet a cross or an obstacle, we basically reset the height to 0 again. Otherwise, we'll keep on increasing the height by 1. So here's the code. It's very simple to code. So first of all, we would have these inputs read in, and then I will create this 2D array here. And I subtracted the rows and column numbers by 1 because this row and column starts at 1, so it's 1 indexed, but I changed it to so that's 0 indexed. So I will use this Boolean array, and it will be true if we have an obstacle at that position. And then this v will be used to keep track of our height. So here I gave it a size of c. So basically c is this column number, which is what we're keeping track of, since we're looking down the rows like this way. So we should keep track of the height in each column. And here we will use 2 loops here. The first one will loop through the rows, and then for every column inside this current row, we will check if this is an obstacle. If the position at this current row and column is an obstacle, we should reset the height to 0. Otherwise, we increase the height by 1. So basically, like what we did here, if it's an empty column or if this is an empty grid, we should increase the total height of this current column by 1. Otherwise, if it's blocked off, it should become 0 again because we cannot form any rectangles on an obstacle. And then for each of these rows, we will get the maximum rectangle. So this maximum rectangle will find the answer in O(n) time. And here we use our stack, like what I said. And here at the end of this vector, I pushed back the height of 0 because this is basically what we're looking at, this extra 0 here. So then this 0 will be smaller than or equal to everything here inside rectangle, so it will pop out everything at the end and calculate everything. So this is what this 0 does. And then here we should push back the indexes of each of the height, because we can just access the height by looking at the index, so we just need to push back the index. And this n will keep track of our maximum rectangle for these current heights. So we loop through each of the columns, but we have here, instead of going from 0 to to c minus 1, we should go to c, because we increased this element by 1. And then we should check if this current stack is empty, that means there's nothing in front of it, so we should just continue on to the next element. Otherwise, we can check if the height at this current position that we're looking at is greater than or equal to our current position. So basically, if our current position is, like, say here, it will be smaller than the previous position, so we should perform our calculations on finding the height. So first, as I said, we'll get the index of our current position, because this position will give us the height that we're looking at. So we're basically looking at this height here, the element on the top of the stack before what we are currently looking at. And then we pop this back. So now we will get the width by looking at the next element on the top, because we already popped out the topmost element from the top. We're basically getting the element after that, and this will give us the height. This will give us the width by subtracting our current index, which is this index, not the index of the rectangle that we just popped off. We're looking at the current index of the column and subtract it by our by the next value inside our stack, and we have to minus 1 because, as I said here, we're looking at one value before. So here we should get the maximum again. Just multiply the width by the height. The height should be, now we should be looking at the element that we just popped off, because our current index represents the end of this rectangle, so we should look at the height of this rectangle that we're ending at. So we get the maximum of that, and after we go through this while loop, we should push this our current height into the stack again, so we can look at the next one, and then the next one will, so basically the next element will also look at this current height. And here, although we have a while loop inside this for loop, this will give us an ON solution, because the stack will not be, no items will be added into the stack multiple times. So here we're either popping or push 1. So every time we pop, we will decrease the stack size, and so at most, we can have at most n elements inside the stack, and that will just give us n iterations inside here. So no matter what we do, this maximum will still be ON, and so this whole loop will always give us the answer in ON time. So finally, we should return our maximum rectangle that we currently have, and we basically do this for all of the rows. Just sweep through the columns as well, and set the height to 0 if it's an obstacle, otherwise increase the height by 1. So we get the maximum rectangle every time, and also store that in a maximum value. And finally, all we have to do is just print out this maximum value that we have, and that will be the answer.